Now we're getting to a slightly more complicated things. The polarization. So let's continue. I think we kind of go through the linear polarization, sort of. So the first case is so if you have the basis. This just remind you the basis. What we use now. We chose the base according to. So there are three unit vector n, which is the vector of the vector direction of the wave vector. So basically k wave vector is wave number times this unit. And then you choose two unit vector perpendicular and both perpendicular and they are perpendicular to each other. So they form a orthogonal set. So epsilon 1, epsilon 2, and epsilon 1 cos to epsilon 2 give you n. So they are all perpendicular to each other. Okay, so that's the choice of our local coordinate system. Obviously, we give for different n, these are 1 and 2 are arbitrary. You can rotate it. Later on, we'll talk about rotation. You can rotate these two vectors and form a new set so that you have the freedom. But once you choose that, you can now express your electric field in the epsilon 1 and epsilon 2 that's given by 7.19. So, and electric field, you have the polarization is sub 1, epsilon sub 1 plus sub 2, epsilon sub 2. And then you have the phase, that's the usual phase. Okay, so that's combination is the amplitude of the wave, and usually we call that polarization. And the linear polarization is that first we assume all those are real vector. So these are just usual spatial vector. Later on, Jackson already talk about the n can be complex, but now we forget about this complication. For now, just use real vector. So these epsilon 1 and epsilon 2 are, but the e sub 1, e sub 2 can be complex number. Okay, so the idea is that if they have the same phase, so if E1 has the EI, what do you call it? Is it theta one? Is it Jackson? What theta? Jackson doesn't have that. Remember, we can define it. You have the phase theta 1 and E2. That's E2 magnitude, EI theta 2. So the first case is if theta 1 equals to theta 2. So in that case, both the exponential factors are the same. You can pull it out and combine with this the original exponential function that becomes 1 magnitude epsilon 1 plus 2 magnitude epsilon 2. Now this bracket is totally real because this is just magnitude. All the unit vectors are, and then the phase is included in this phase vector. Theta 1 and theta 2 are the same thing. Either one, right? And that is a form of a linear polarization. Okay, so because this is a real vector, and usually when we look at polarization, we go back to the real space. Right, for real space, this one is trivial. A real electric field, take a look, because this is real. The real part is just basically the cosine of this phase function. So it means that you have a vector, whatever this direction. This is epsilon 1, epsilon 2. Then this is just a vector with component e sub 1 at the epsilon 1 direction. we have two in the epsilon two directions, and this a vector. But this is just describing this reaction. So the cosine factor just means that the electric field oscillating back and forth, right? From this, and similarly in the negative direction. So because cosine can go positive, negative, and it's just oscillate like that. Okay. And what I mean is that you like you either you keep x fixed, and then this would be the real part would be just cosine of this phase factor is a function of t only. So it's oscillating, and the frequency of the oscillate is this omega. I mean the circular frequency, or the whatever they got, yeah, the circular frequency. Right. So that's the easiest case of linear polarization. All right. So all right, that so far so good. Now the second case is circular polarization. Now instead of theta 1 is equals to theta 2, now we actually add the phase difference of pi over 2 plus or minus pi over 2, right? Or the other way around, so because you have plus or minus, it doesn't matter, they cover everything. So in that case, obviously, if you pull out theta 1, then theta 2, this part we still have a phase of I pi over 2, which is, you need to have an I. Right? So the first condition is that the phase is different by a pi over 2 phase, right? And in addition, you require that the magnitude are the same. You require this. This is equals to whatever. It's the same. So, right. So if you require that, then the electric field will be simply just pull out the magnitude. Either E sub 1 or E sub 2, they are the same. And then you have epsilon 1 plus or minus I epsilon 2. And then you have the phase. Okay. So that would give you the what we call the circular polarization. So you have two cases. One is the plus sign, the other is the minus sign. Okay. And that is in equation 7.20, but I just assume theta 1 is 0. All right. And to see that it's circular polar and how it rotates, we need to go back to the real phase. But before we do that, there's a usual definition. Instead of defining this real unit vector, you define this complex unit vector for circular polarization. You define epsilon plus or minus, the subscript with plus or minus, defined as epsilon 1 plus or minus epsilon 2. But you normalize that with 1/2, right? That is how you define this epsilon plus or minus. And what we mean by normalize that, obviously, look, there's an I. Yeah, they're out 90-degree out of phase, so there's an I. Okay, and so they are complex because epsilon 1 and epsilon 2 are real. So with the I here, they becomes complex. And what we mean by the normalization is obviously they can, if they dot into itself, it's still complex. And so instead of epsilon like epsilon plus or minus dot into epsilon plus or minus, they are still complex, but you multiply by its complex conjugate, then say epsilon plus or minus, then in this case, you can work that out. So this dot in complex quantity, you basically reverse the sign. So if basically epsilon 1 plus I epsilon 2 dot into epsilon 1 minus I epsilon 2, right? So you have four terms. Epsilon 1 dot into epsilon 2 will give you 1. And I epsilon 2 dot into minus I epsilon 2 also give you 1, right? But then epsilon 1 dot into epsilon 2 or vice versa, they're 0 because they are all orthogonal, these two vectors. So you have 2 in the denominator and the factor, because you have two factors. You have 2 square of 2 in the denominator, so multiply to 2, and you have 2 in the denominator and 2 in the denominator, 2 in the numerator, so that altogether. Check that right away. Okay, so that's why we are normalized that with this square root of 2 factor here. So this is a normalized this vector with a compact conjugate. And you can also check that epsilon plus dot is epsilon minus. They are orthogonal. That's you can check it in a straightforward manner. Right. So like I should say, I mean, it's not normal this way. So it's normalized in the original one. So epsilon plus or minus dot epsilon 1 or 2. Right. Yeah, it's normalized also with the complex conjugate. Also with the complex. So epsilon plus complex conjugate dot into epsilon minus, you still need the complex conjugate. Or vice versa, if you have a minus, you dot. So basically, that is basically epsilon 1 plus. So for this one, epsilon plus complex conjugate basically becomes epsilon minus squared. So epsilon 1 dot into epsilon 1 is 1, but then minus epsilon 2 dot into minus epsilon 2 gives you minus 1, so 1 minus 1 is 0. And epsilon 1 dot into epsilon 2 is 0, so they will be automatically 0 this way. Right? So this is another. And obviously, they are still perpendicular to n, and that is trivial because both epsilon 1 and epsilon 2 are perpendicular to n. So these are the unit vector for circular polarization. So in this case, if you assume this electric field is just simply, this electric field is simply either this epsilon 1 epsilon plus or the other way around. So this plus or minus sign basically you have two cases. The original is a combination of two fixed unit vector, but if we assume the magnitude are the same, and then the phase are the same, the phase are shifted by pi over 2. The phase are shifted. Then this becomes either this one or that one. It depends on how you shift it plus or minus pi over 2. So you have either cases. So, all right. So they are purely in either epsilon plus or epsilon minus in this case. Obviously, you can also add a combination of cases like that. Say you have this one multiplied by this one multiplied by another magnitude of a complex number. We'll talk about that general case later, but for the special case, we're talking about this. So now we want to see why this is circularly polarized. And how to sense of polarization for these two cases, epsilon plus and epsilon minus. Okay, so to do that, we need to go back to the real electric field and look at how the field change. Okay, and let's see. Let's move a little bit over here. So the field are either this one or that one. Epsilon plus or minus is given by this one, divided by square of 2. All right. So the wheel of electric field, which is what usually we mean implicitly when you write down a compact expression. We usually implicitly assume that the physical quantity afterwards you are taking the wheel part anyway. But now to see the physics is easier to do that in real space now. It's obviously you have the like epsilon plus or minus. So combining these two cases is basically epsilon plus or minus. So the magnitude obviously is real. And then you have square root factor, right? And then you have two complex numbers multiplied together. So this is a complex number, a complex vector actually. And multiplied by the phase is also a complex number. So basically you have, for the real one, you have the like epsilon 1 multiplied by the cosine of this number. You have epsilon 1 times cosine of dot x. Well, this is just a phase. Let's just keep it general for now. Later on, we'll just choose some special value to look at it. And so that would obviously will be real. Then you have this I, this is purely imaginary. And you need to multiply by the imaginary part of this exponential function, which is I times sine of this one. So I times I is minus 1, so it becomes minus plus. Minus plus epsilon 2 sine of dot x minus omega t a phase. Okay. All right. So that's the real part. Is that okay? So now we just look at what it means. We can first look at for a fixed location, fixed x, and then look at how it changed in time, how this vector changed in time. Right? We can start from t equals 0. So start from t equals 0, that is 0, that is 0. If we choose a location such that k dot x plus theta 1 is 0 also, then if this will be 1 and this will be 0. Right? Is that okay? So we just make our choice. Now look at the location x such that this two phase add up to the 0, and look at t equals 0. At this location, we're looking at this is directly epsilons of 1, epsilons of 2. Okay. Then this component is 1, this component is 0. So this is a vector. The electric field is like that. And this is the magnitude, whatever this magnitude is. This is one magnitude, compact magnitude, divided by square of 2. So that's this length of this vector. Okay. Okay, so we start with that. Then we look at a little bit later. This is t, or is it white? This is t equals 0. Okay. And then I increase t by a little bit. We increase, this is a even function, cosine even function, but it's obviously it will be still close to 1, but a little bit less. So this doesn't matter. And now we look at that. So with t increased by a little, so this would be a negative value, but a small negative value. The sign is for small value, just the value itself is still negative. So sign is also negative. If that is negative, and you multiply by negative or positive. So when the negative case becomes plus, so you have a little bit of epsilon 2 component for the plus case. The vector, obviously, the magnitude is still the same because they are cosine and sine function. Cosine squared plus sine squared is 1. So we move along a circle, but you have a little bit of epsilon 2 component. So this is t greater than 0, but for the plus case, for this plus k, which is give you minus. Remember the epsilon plus is this one. Epsilon plus has a plus sign here, but then this is coming from taking the real part and flip the sign to minus plus. But for a little bit of positive t, but this is negative, and flip the sign again to become positive. So this is a plus sign, and the vector move in this way. Okay, and obviously for the plus sign here, which is the epsilon sub minus, that is plus and sign is minus, and you have a little bit of negative epsilon 2 component. This is for t greater than 0 for the minus sign. Okay, then obviously as t keep going, then you can see that this vector just rotate this way and keep rotating as this sinusoidal function. And likewise, this negative one will start from here, moving to this, and then keep moving. You increase in time, moving in along this circular, the circular path, right? So that's how we see that it's a circular polarization, because the electric field vector is just rotating in time and tracing a circular path. Okay, is that okay? So that you can see that it's circular. Why it is circular? But then now come the point that we give them names, epsilon plus and epsilon minus. This is first we need to determine the n direction. This epsilon 1, epsilon 2, and n direction is epsilon 1 cos epsilon 2. So epsilon cos epsilon 2 is the direction that going out of the board. The n direction is going out of the board. Okay. Now this the plus sign is rotating. This is counterclockwise, and also the wave propagating direction n is in the out of the board. So you use a right hand, use a thumb as the propagation direction, and the finger is rotating counterclockwise. So if you define whether the wave define according to the n is along the thumb direction, the finger direction determines the which hand you use for the fingers direction represent the rotation direction. That is the what we call the define the way. So you use the right hand this way, then you call this right hand polarization. So this you call it right. If the n is pointing in the direction of the thumb, and likewise it would be you need the left hand with the thumb along n, and the rotation directions are the finger, and that would be left. Okay, and so that is many people define like that, including possible physicists. In other cases, like engineer and all that. And Let's see, Jackson, talk about that. Left and right. Let's talk about for the plus sign, epsilon 1 plus I epsilon 2 rotation. And so this is, in modern physics, this is called partial helicity, or the right hand. So this is according, using what I said. But Jackson also mentioned that usually, I mean, in optics, they define it in totally opposite sign. They're basically looking at using the thumb pointing in the direction that you observe the source. So basically, the wave is propagating towards you, and then you point your thumb towards where the wave coming from. And in this case, this one is the direction of the fingers. So optics will call this right. So this is optics. And this obviously is the other way around, left for optics. Okay. So that's an unfortunate fact. So they are totally opposite definition or totally opposite convention. It seems like they are not in any any time soon. They will try to reconcile this. What is happening? Hopefully this doesn't block my. Some windows just pop up. Okay, but we just need to be a little careful when we read the literature how people define left polarization, right polarization, and just be aware that there are two totally opposite definitions out there. Okay, so and depends on context. Most of us work on plasma physics. I mean, it's at this place. I mean, even modern physics, high energy physics or quantum people are using the same notation. Like the helicity is defined by the pointing the thumb at the propagation direction. Okay, so or the particle direction in quantum is a particle wave, basically the same. So, so you define the helicity of the particle according to the propagation direction in the thumb, and the helicity, whether it's rotating in the right or left, according to the finger. So it's the same as the first definition, not the optics. So in most physics, it's okay except optics. Okay, so is it clear enough the definition of left and right and that?